So what Charles' law tells us is the relationship between volume and temperature. So if you look here, notice if I have a temperature of 200 Kelvin and a volume of 1 liter, if the temperature increases to 400, notice what happens to the volume of the gas. The volume of the gas is going to increase, and that's because the particles are moving more quickly. And so the gas is going to expand out. Now, if you think about it, when temperature increases, volume also increases. What type of relationship is this? Well, this is a direct relationship. When one goes up, the other one goes up as well. Now, the equation for this is going to be V1 over T1 equals V2 over T2. Okay. The only quirky thing about Charles' law when we're dealing with temperature is that the temperature must be in Kelvin. And the reason why is Kelvin, the absolute coldest Kelvin can ever be is 0. We will never actually reach 0, but that is considered absolute 0, which is good because a lot of the time we will have values for temperature in Celsius that are negative. Well, if you have a negative temperature in this equation, that makes no sense for your volume because your volume could end up being negative, which doesn't make sense. So having Kelvin enables us to do these calculations because the Kelvin measurement can never be negative. Okay? So remember, to go from Celsius to Kelvin or Kelvin to Celsius to do that conversion, remember the temperature in Kelvin equals the temperature in Celsius plus 273. Okay, so let's look at 2 quick examples. 300 Celsius, and I'm asking you to convert that into Kelvin. Well, I need to take my temperature in Celsius, 300, and I'm going to add that to 273, and that will give me my temperature in Kelvin. So I get 573. Okay, let's look at the next one. 25 Kelvin. I'm actually going to write this one out. So my temperature is in Kelvin, so 25 equals TC, temperature in Celsius, plus 273. So to solve for my temperature in Celsius here, I need to take 25 and I need to subtract 273 from it. And what I get is negative 248 degrees Celsius. All right, so there are 2 more practice problems for you to do here. So let's look at 2 examples of actually applying Charles' law. It tells me that a balloon is inflated in a room at 24 degrees Celsius, so that's going to be my T1, my first situation, my temperature, with a volume of 4 liters, V1. It then tells you that the balloon is heated to a temperature of 58 degrees Celsius. So this will be my T2, and it wants to know what the volume will be. So let's write out my equation for Charles' law. V1 over T1 equals V2 over T2. My volume is 4.00 liters. Keep in mind your temperature has to be in Kelvin, so I need to take 24 degrees Celsius. And remember, your temperature in Kelvin equals TC plus 273. So I'm going to take 24 and I'm going to add it to 273. So my temperature in this case is 297. That's going to equal my V2, which is what I'm solving for, all over, well, 58 plus 273 will be my new temperature, so 331. All right, so what I'm going to do is I'm going to cross multiply. So these multiplied by each other will equal these multiplied by each other. So let's write that out. So 297 times my V2 equals, well, I'm going to take 4 and multiply by 331, and I get 1,324. And now I need to take both sides and divide by 297. Divide by 297. And keep in mind, I'm going to keep everything in my calculator. My V2 equals 4.458. Let's figure out sig figs. So I've got, keep in mind here, the 24 is not what you use for sig figs. Because you then add 273 to it to get the 297, your 297 is what you're going to use for sig figs. So I've got 3 sig figs here, 3 sig figs here, and 3 sig figs here. So use your temperature in Kelvin for determining sig figs. So I need 3 sig figs, 1, 2, 3. So this is going to round to 4.46. Keep in mind my units for volume were in liters, so this is going to be liters. Let's make sure this answer makes sense. So I go from a temperature of 24 degrees to 58 degrees. So my temperature is increasing. My volume should also increase because, according to Charles's law, volume and temperature are directly related. It does increase, so I know that I did the correct work. All right, let's look at one last practice problem. It says a gas at 65 degrees Celsius, my T1, occupies a volume of 4.22 liters, my V1. At what temperature in Celsius will the volume be 3.87 liters? So that is my V2. So I'm going to set this up. V1 over T1 equals V2 over T2. My V1 is 4.22. Keep in mind, my T1 is currently in Celsius. It needs to be in Kelvin to do this calculation. So I need to add 273 to it. So this is 338. Just because I ask for your temperature in Celsius does not mean you can leave anything in Celsius. You will get the wrong answer. I will show you what you need to do in 1 second. So 3.87 is my V2 all over my T2. So I am going to cross multiply. Okay, and so what I end up getting is 4.22 times T2 equals, I need to take 3.87 and multiply it by my temperature, 338, and I get 1,308.06. And then the last step I need to do for this part is divide by 4.22. Then I have my T2 is 309.96. Here's the problem. Right now, I am in Kelvin, and I want to be in degrees Celsius. So remember, your Kelvin equals your temperature in Celsius plus 273. What I need to do to solve for my temperature in Celsius is I need to take my temperature in Kelvin, 309.96, and subtract 273 from it. And what I get is 36.97. You might be tempted to round based on sig figs, but notice the last step that you're doing is subtracting 273. So you need to be rounding based on decimal places. 273 has no decimal places, so I'm just going to want to keep the 3 and the 6 places because I want no decimal places. So this is actually going to round to 37, and my units are degrees Celsius. So far, I've introduced two gas laws: Boyle's law, which relates pressure and volume, and Charles's law, which relates volume and temperature. I've got two more gas laws to introduce in this lesson, and that's Gay-Lussac's law and then the combined gas law. So Gay-Lussac's law relates pressure and temperature, and specifically it lets us know that pressure and temperature are directly related. And we can actually see that by looking at this drawing here. So if I have a gas that's at 200 Kelvin and a pressure of 1 atmosphere, if I increase that temperature, what happens is the molecules are going to be moving more quickly. So as those gas molecules move more quickly, they're going to collide with the sides of the container more frequently and with more force, which is going to cause the pressure to increase. Notice one thing, and I will address this when I get to the combined gas law, but do notice that the volume is not changing if I'm using Gay-Lussac's law. All right, so just like with Charles's law, which showed a direct relationship between volume and temperature, for Gay-Lussac's law, the formula is going to be the following: P1 over T1 equals P2 over T2. And keep in mind, just like with Charles's law, the temperature must be in Kelvin. All right, so let's look at some examples here. All right, so for example 1, it says a gas system has an initial pressure and temperature of 12 atmospheres, so that's my P1, and a temperature of 27.9 degrees Celsius, so that's my T1. If the pressure changes to 3.74 atmospheres, that's my P2, what will the resulting temperature be in degrees Celsius? Okay, so I'm going to use my formula P1 over T1 equals P2 over T2. I'm going to plug in my P1 is 12.0. My T1 I'm given it in degrees Celsius. So what I need to do, remember, to go from degrees Celsius into Kelvin, I need to simply add 273 to my temperature in Celsius. So I'm going to do that right now. So 27.9 plus 273, and I get 300.9. So I'm not going to round this. I'm going to just keep it as it is. That equals my pressure in my second situation, which is now 3.74 atmosphere. So my pressure has decreased, and I'm being asked to solve for my new temperature. Okay, so I'm going to cross multiply. So what this gives me, I have 12.0 times my T2, and that equals 300.9 times 3.74. And that is unrounded 1,125.366. Now I'm going to take 12.0 and divide both sides by that value to get T2 all by itself. Okay, and what I get for my temperature, unrounded, is 93.7805. So 93, I'm going to just round to 93.78. Keep in mind this is in Kelvin, but I want to be in Celsius. So what I now need to do, since I have my temperature in Kelvin, to determine it in Celsius, I simply need to subtract 273 from it in order to get my temperature in Celsius. So I get, for my temperature, negative 179.22 degrees Celsius. Again, you might be tempted to round based on sig figs, but keep in mind, because my last step is subtracting, I need to round based on decimal places. So 273 has no decimal places, so I'm just going to keep the 9 there. And so this is just going to round to negative 179, and my units are degrees Celsius. All right, let's look at the next example. A gas system has an initial temperature of 170 degrees Celsius with the pressure unknown. So this is my T1, and it says the pressure for that initial situation is unknown, so that's going to be my P1. When the temperature changes to 1,117 degrees Celsius, so that's my T2, the pressure is found to be 7.77 atmosphere, so that's my P2. What is the initial pressure in atmosphere? So P1 over T1 equals P2 over T2. I don't know my P1, so I'm going to put it up top. I do know my T1, it's 170 degrees Celsius. So I need to take 170, and I'm going to add 273 to that to get it into Kelvin. So I get 443. Okay. That equals my P2, which is 7.77, all over my T2. Well, my T2 is 1,117. I need to add to that 273 to get it into Kelvin, and I get 1,390 Kelvin. And now I can solve this. So I'm going to cross multiply. Okay, so 1,390 times P1 equals, so well, 443 times 7.77. And I get 3,442.11. I'm going to divide both sides by 1,390. And my P1 that I get, unrounded, is 2.476. Okay, sig fig wise, remember I'm not going to use 170 to determine sig figs. I'm going to use the 443, that temperature in Kelvin. So I have 3 sig figs here, 3 sig figs here, 3 sig figs here. So I need 1, 2, 3 sig figs. So this is going to round to 2.48 atmospheres. I'm going to really quickly go back to the first example problem and make sure that both of these answers make sense. So remember, for the first problem, you are decreasing your pressure. So if you decrease pressure, that means your temperature should also decrease. Well, my temperature goes from 300.9 Kelvin to 93 Kelvin, or from 27.9 to negative 179. So my temperature is decreasing, which is what I would expect. For the next example, notice I'm increasing temperature, going from 443 to 1,900. So this pressure here, my initial pressure, should be lower than 7.77. And it is, it's 2.48. So that's a nice, easy way to be able to check your math. All right, so the combined gas law. Basically, as you can see from this table, all of my gas laws are derived from one gas law, which is your combined gas law. So P1 times V1 over T1 equals P2 V2 over T2. So you will use your combined gas law when you are changing all three of the variables, P1, V1, and T1. If you're not, if one or two properties of that gas are being held constant, then you'll have one of the three laws we've already looked at. So for example, if you're keeping temperature constant, okay, if you get rid of temperature, you've got Boyle's law. If you're keeping pressure the same, you have Charles' law. And if you're keeping volume the same, you've got Gay-Lussac's law. So let's look at two examples where we're actually changing all of our variables, pressure, volume, and temperature. So it says a child has a toy balloon with a volume of 1.80 liters. The temperature of the balloon when it was filled was 20 degrees Celsius, and the pressure was 1 atmosphere. If the child were to let go of the balloon and it rose 3 kilometers into the sky, where the pressure is 0.667 atmospheres and the temperature is negative 10 degrees Celsius, what is the new volume? So notice, this is my V1, this is my P1, and this is my T1. Those are my initial conditions. Then my pressure will decrease, so that's my P2. My temperature is going to also decrease because that's what happens when you go up high in the atmosphere. And then I'm solving for my V2. The 3 kilometers is just extra information that you will not actually need to calculate this. So since I'm changing all 3 variables and not just 2, like I did for the 3 other gas laws, I need to use my combined gas law. So P1 V1 over T1 equals P2 V2 over T2. Okay, and now it's just a matter of plugging and chugging. So 1 atmosphere, my volume is 1.80. Remember, my temperature needs to be in Kelvin, so I'm going to take 20 degrees and add 273 to that, and I get 293. Okay, my P2 is 0.667. I don't know my V2, so I'm solving for that. And then I'm going to put that all over my T2, which is negative 10. So negative 10 plus 273 is 263. Now, keep in mind one thing that I haven't really been talking about, other than with Kelvin, is units. Keep in mind, since my units for pressure, for both of my pressures are atmospheres, no conversions are needed. And I know that my units for volume will be in liters. Since this unit for 1.80 is in liters, then this volume has to be in liters as well. I'm going to cross multiply now. All right, so what that gives me, I'm going to take 293, and I'm going to multiply that by 0.667 times V2, so I get 195.431 times V2, and that equals, so I'm going to take 1 times 1.8 times 263, and I get 473.4. Now I'm going to divide both sides by 195.431. And my volume that I get, unrounded, is 2.422. Okay, sig figs. Let's look here. 1.00 has 3. 293 has 3. 0.667 has 3. And 263 has 3 sig figs. So 1, 2, 3. So 2.42. And my units are going to be liters. So notice there are 2 counteracting factors in this when we look at what happens to the volume. So when the balloon rises, its volume increases. It goes from 1.80 to 2.42. Why? Well, the pressure is decreasing, which means the volume should increase. But the temperature is decreasing, which would cause the volume of the balloon to decrease as well. Because remember, pressure and volume are inversely related, but temperature and volume are directly related. So clearly the effect of the pressure decreasing is more significant than the effect of temperature decreasing, which is why the volume of a balloon when it rises up in the sky will increase until it eventually pops. And keep in mind, when a balloon rises up in the atmosphere, remember, the higher up in the atmosphere you are, the lower the pressure is. All right, let's look at example 2. I have 17 liters of a gas at a temperature of 67 degrees Celsius and a pressure of 88.9 atmospheres. What will be the pressure of the gas if I raise the temperature to 94 and decrease the volume to 12 liters? So since I'm changing 3 variables, I'm using combined gas law. This is V1, this is T1, this is P1, this is my T2, and this is my V2. All right, so my pressure is 88.9 atmospheres. My volume is 17 liters. And my temperature, I need to take 67 and I need to add 273 to that. So I get 340. And I'm going to put 340 point because I just don't want any decimal places, but I want all 3 of these numbers to be significant. Okay. My P2 is what I am solving for because it asks what the pressure is. My volume, it's decreased to 12 liters. Notice my units for volume match up, so I'm good there. And then my new temperature, 94, I need to add 273 to that. And the value I get is 367 Kelvin. Okay? So what I'm now going to do is I'm going to cross multiply. So 340 times 12 times P2 gives me 4,080 times P2. That equals, well, 88.9 times 17 times 367. It's a very large number, 554,647.1. I'm going to divide both sides by 4,080. Okay, and the P2 that I get is 135.9. Keep in mind, 88.9 has 3 sig figs, 17 has 2 sig figs, 340 has 3, 12 has 2, 367 has 3, so I want 2 sig figs. So this is just going to round to 140. Let's figure out what my units are. Well, the units for pressure for P1 are atmospheres, so P2 must also be in atmospheres.